Question 7 says, which of the following series converges absolutely? We can ignore all these negative 1 to the n's. If the series need the negative 1 to the n to converge, then they don't converge absolutely, they converge conditionally. So for the first one, we're going to say, when n becomes large, the most powerful term on top is n root n, that 2 is insignificant, and the bottom most powerful term is n squared. And that's equal to root of n over n, canceling 1 power of n, and that's equal to 1 over root n. And that is p series with p less than 1, so it diverges. P is equal to 1/2. So A, even though it converges conditionally, because at negative 1 to the n, this will pass the alternating series test and all that other good stuff, it doesn't converge absolutely. Next one, B. So B is going to go as, most powerful term on top is root n, most powerful term on the bottom is n squared, which is equal to 1 over n to the 3 over 2. This is 4 over 2, this is 1 over 2, and subtracting 3 over 2. This is p larger than 1, so it converges absolutely. Doesn't need the negative 1 to the n to converge. So the choice is B, with a check mark beside it. Let's go through the rest of them. C, n factorial over 2 to the n. So this time we can't do this asymptotic thing. N factorial doesn't have a, well, it does. It's that Stirling's approximation that I mentioned in class and gave you the formula for it, but I don't think you're supposed to use it. I'm not sure what would happen if you did. You'd probably be horrified and say it was wrong, even though it's not. But anyways, the right way to show that this diverges, which it does, is using the ratio test, which we calculate L equals absolute value of a sub n plus 1 over a sub n. We want to just make sure that this is less than 1 for it to converge. And if it's larger than 1, it diverges. And if it's equal to 1, it's ambiguous. So we're going to have absolute value of n plus 1 factorial over 2 to the n plus 1 divided by the original function. So that's going to mean 2 to the n on top over n factorial on the bottom. Dividing means multiply by the reciprocal. Everything in here is positive, so we can drop this absolute value stuff. I'll reorder the terms, n plus 1 factorial over n factorial, 2 to the n over 2 to the n plus 1. That's just changing the order, multiplication. And n plus 1 factorial we can write as n plus 1 times n factorial. That's like saying 7 factorial is equal to 7 times 6 factorial. Bottom is the same. And then on the right side, we can use exponent laws to write 2 to the n plus 1 as 2 to the n times 2 to the 1. Let's start canceling stuff. Cancels. We get n plus 1 over 2. And as n goes to infinity, this goes to infinity. So there should be limits in front of all these. I'm lazy. Limit as n goes to infinity. Should be limits in front of each one, each line. I'll write that out. Even though it's multiple choice, it doesn't really matter. Okay, so this diverges. So it can't be C. And then D, that's a P series with P less than 1, so it diverges as well. So the choice is indeed B and only B. Number 8. Okay, which of the following series diverges? So let's go through. This one here is the reciprocal of what we just did. We could go through a ratio test and show it converges, so I'll do that. L equals the limit absolute value of an plus 1 over an. It's the limit of 2 to the n plus 1 over n plus 1 factorial multiplied by the reciprocal of this. So we're dividing by this. So n factorial over 2 to the n. We get limit of 2 to the n times 2 over 2 to the n. Just change the order of the multiplication, just like the previous one. N factorial over n plus 1 times n factorial, just like before. Cancel the n factorials, cancel 2 to the n's. We get the limit of 2 over n plus 1, which is equal to 0, and 0 is less than 1. So converges absolutely by ratio test. So it's not going to be A. A converges, doesn't diverge. How about B? 1 over n to the n. Lots of ways to do this one. Root test, ratio test. Ratio test involves a nasty limit. Easiest way is 1 over n to the n. That looks like the sum of 1 over n to the n looks like 1 over 1 to the 1 times 1 over 2 to the 2 plus 1 over 3 to the 3 plus all the way up. And let's compare it to 1 over n squared. Which is bigger? 1 over n to the n or 1 over n squared? Well, when n is larger than 2, or larger than or equal to 2, 1 over n to the n is going to be smaller. So compare the 1 over 3 to the 3 to 1 over 3 to the 2. Definitely smaller. And that's 4 n larger than 1. Now, 1 over n squared converges, since it's a p-series, with p larger than 1. And if the larger series converges, then the smaller series must converge as well. By the comparison test. And it's definitely true that 1 over n to the n is less than 1 over n squared. For the same rule, we could cross multiply if you want. N squared is less than n to the n. And that's true for all n greater than 1. So it's not B. Definitely converges. Converges very quickly, much more quickly than 1 over n squared, 1 over n cubed, or even 1 over n to the 10,000 for n larger than 10,000. Next one. For C, this goes asymptotically. It's a whole bunch of polynomial stuff, so it's easy to do this as n to the 7 over n to the 9, which is equal to 1 over n squared. So you could do a comparison test or a limit comparison test with this if you wanted to show it properly. LCT would be the easiest one. Make the ratio and you'd get a limit of, limit of 1 in this case, which is less than infinity, and that's all you need to show that it does the same thing as its comparison function, which converges. Converges by limit comparison test would be the way to show it. So that one doesn't diverge. How about D? D goes as sine. Well, we can't do much to it. Sine of n over n to the 1.1, and that is going to be less than 1 over n to the 1.1 because sine of n, or rather the magnitude. Well, no, even without magnitude, because sine of n is between -1 and 1. Strictly speaking, we're not going to get -1 or 1. We're plugging an integer into sine. We need to plug some integer multiple of even integer multiple of pi over 2 in there. So, and we're not going to get that from an integer. This pi is transcendental, but I'll keep the equal signs there anyway. So whatever we multiply by, we're multiplying by a number that's smaller than 1. So it's going to give us something that ends up being smaller. And this, 1 over n to the 1.1, converges because it's a p-series with p larger than 1. So by comparison test, it converges. A sub n converges. So it's not D. That means it's none of the above. All of them converge. None of them diverge.